Hello Algebra 2 Trig students, welcome back. We are on lesson 2 of unit 3, polynomial functions, and our focus today will be on graphing and creating polynomial functions. So we're going to graph a polynomial function, and we should be able to look at a graph of a polynomial function and create the actual equation. You can do your little warm-up, maybe you want to pause and see how you did. So go ahead and pause. Okay, how'd you do? Writing in descending order. Remember, you go from highest degree to lowest. So you should have restructured this to become negative 4x cubed plus 3x squared minus 2x plus 5 equals p of x. Therefore, we look at the highest power, which is 3, so it has a degree of 3. The leading coefficient is negative 4 because it's the coefficient in front of the highest power. And then our end behavior. So your end behavior is as x goes to infinity, what is p of x going to do, or what will the y value go to? Or as x goes to negative infinity, what is the y value going to approach? So I just took this leading coefficient and the first term, and I plug in a negative infinity. If I plug in a really huge negative number and I cube it, well, a negative times a negative times a negative is negative. And I multiply that by a negative 4, that's going to turn into a huge positive number because 4 negatives multiplied together become a positive. Here, if I have a positive huge number and I cube it, it's going to be a positive huge number, even bigger than what it started with. And then I'm going to multiply it by a negative 4, so it's going to turn into a negative huge number. So, oops, I reversed those, sorry. As x goes to positive infinity, that's the green one, it should go toward negative infinity. And as x goes toward negative infinity, it's going to go toward positive infinity. Sorry about that, I swapped them. All right, so now we're going to talk about some graphs. So the next thing we do is the multiplicity of a root in a polynomial function. So what do we mean when we say the word multiplicity of a root? So it says every root has a multiplicity, which refers to the number of times that its associated factor appears in the polynomial. For example, if we have a function f of x and we take x minus 5 and we square it, and multiply that by x plus 3, then x equals 5 is going to be a double root because it has a multiplicity of 2. So it has a multiplicity of 2, it appears twice, therefore we now call 5 a double root. And you'll just see us do stuff like dr. And then negative 3 is to the first power, so that doesn't have more than one value of negative 3, so that's just a single root, right? So we have a double root. It has a multiplicity of 2 because that factor is raised to the second power. And then we have a single root. It's just a multiplicity of 1. Now, we have two very important things you must remember, especially when we're thinking about things graphically here, when we're thinking about the polynomial function graphically. The first one is if the root has an odd multiplicity, so it's to the first power or the third power or the fifth power, that's an odd multiplicity, then it will cross the x-axis at that root. So x equals negative 3 had an odd multiplicity, it's raised to the first power, so your graph would cross the x-axis at negative 3, right? So it's going to cross here. If it has an even multiplicity, the graph will bounce off. It will not cross the x-axis. Instead, it bounces away. So positive 5 has a even multiplicity, and so it's going to bounce away there. So we'll talk more specifically about why I know the graph looks like this, but it's going to be something squared to the first power. It's going to be a cubic function. It's going to go through negative 3 because that was a single root. Then it's going to come down to the positive 5 and bounce away because it had an odd multiplicity. An even multiplicity. This is a double root. At double roots, they bounce away. This is a single root. At single roots, they go through the x-axis. So your graph for x minus 5, the quantity squared, times x plus 3 would look something like this. And again, we'll learn more about the details about how I know that as we continue through this lesson. So the next sentence is important. It says, as the multiplicity of a root increases, the graph flattens out more and more near that root. So this was a double root up here, so it just kind of bounces away. But if it's a single root, it just crosses through. If it's a double root, it bounces away, so it's a little bit flatter at that root. If it's a triple root, it crosses through at that root, right? So these are all x equal 1. This is a double root. This is x equal 1, but it's a triple root, so it has a multiplicity of 3. This is x equals 1. It's a quartic root, quadruple root. And so as it goes through, it flattens out. So here it comes down, flattens out, and goes up, but it bounces away because it's a multiplicity of 4, which is an even multiplicity, so it bounces off the x-axis. An odd multiplicity crosses through the x-axis, but again, the higher the multiplicity, the more the graph flattens out at that particular root. So here an example, we could just have f of x equals, some kind of slope minus 1, x-axis goes through. Here we could just have it as x minus 1, the quantity squared. Here it could be x minus 1, the quantity cubed. And here this could be x minus 1, the quantity to the 4th power. So might look something like that. And these are possible equations of these functions, not the actual ones, right? This is just a possibility. Okay, so let's talk more specifically again about end behavior. So we're going to revisit end behavior with respect to polynomial functions. So we have end behavior. It's the way a function behaves for very large values of x or very small values of x, meaning very large values of x, this is as x goes to infinity. Very small values of x is as x goes to negative infinity. We need to look to the far left as x approaches negative infinity. We need to look to the far right as x approaches positive infinity. And we need to figure out what the y value is doing when it's doing that. So we use the plus or minus sign to help indicate if it's going to positive infinity or negative infinity. Now, if we have an odd function, right, f of x equals x to the 1st power, or x to the 3rd power, or x to the 5th power, x to the 7th power, something like that, we have a function with an odd exponent, then what's going to happen graphically? If we have an odd function with a positive leading coefficient, right, this is a positive number, positive leading coefficient, then when we put in a positive infinity, we take a positive infinity to an odd power, well that's still positive infinity, and we multiply it by a positive number, that's just going to go toward positive infinity. If we take a negative infinity to an odd power, well negative times a negative odd number of times is going to stay negative, and if we multiply that by a positive leading coefficient of something like 3, then it would be still a negative infinity. So if you're going to graph that, I just want you to have an idea of what that graph is going to look like. So if I were to graph that, then I'm going to have something that looks like this potentially, right? As x goes toward negative infinity, y goes toward negative infinity. As x goes to positive infinity, y goes to positive infinity. That is an odd function with a positive leading coefficient. Now, if I were to have an odd function with a negative leading coefficient, what will change? Well, now we're talking about a negative leading coefficient, or a negative 2x to the 3rd power, or a negative 2x to the 5th power, some kind of odd exponent, but a negative leading coefficient. So this time when I take my positive infinity, so as x goes to positive infinity, I'm going to have positive infinity to an odd power, which stays positive. But now I multiply it by a negative leading coefficient, so that switches these results to their opposites, right? A negative infinity raised to an odd power is going to stay negative, but if I multiply it by a negative leading coefficient, it's going to change to a positive. So this time, my graph is going to look something like this, an odd function. If I'm going to positive infinity with a negative leading coefficient, I would end going down to negative infinity. If I'm going toward negative infinity, but I have a negative leading coefficient, then my y values are going to be getting more positive. So if you have a positive leading coefficient and it is an odd function, then you're going to be increasing at the beginning and increasing at the end. If you have an odd function with a negative leading coefficient, you are decreasing from the beginning and decreasing toward the end. So you're walking downhill with an odd function, negative leading coefficient. You're walking uphill from the start, positive leading coefficient, odd function. Now an even function, you should be thinking of a quadratic, right? That was an even function, and that was when we either opened up or opened down. So a positive leading coefficient, what happened to the parabola? It opened up. With a negative leading coefficient, what happened to the parabola? It opened down. A parabola is an even function. An even function has even numbers for the highest exponent. So if you have a positive leading coefficient, then what would that do? It would go to positive infinity and negative, as it goes to negative infinity with a positive leading coefficient, it's still going to go to positive infinity. So graphically, what does that look like? If it was a quartic, it might look something like this, right? The end behavior is going up and up. Positive, your end behaviors have to be going, an even function, your end behaviors have to be going in the same direction. An odd function, they go in opposite directions. Right, one's increasing, the other one's decreasing. For even functions, it's the same. And finally, for an even function, if you have a negative leading coefficient, then your end behaviors are going to be going down. So you might have something that looks like that. So it's the same, down, down, for both end behaviors. So as x goes to positive infinity, y is going down. As x goes to negative infinity, y is going to negative infinity as well. Now it's your turn to just sketch and do some of these graphs on your own, see how you do. I wouldn't really worry about the leading coefficient. We're just trying to figure out what graphs would look like. So let me take you through a few and then you can kind of experiment. We're just doing quick sketches to try to get our heads around what these different polynomial functions, what options we could have. So if you have a linear function, you could draw so many different pictures, but there's a one real root. So here is my one real root. It's only going to cross the x-axis at one place. That's the maximum it can cross the x-axis, right? So this is the maximum number of times it can cross the x-axis. For a quadratic, the maximum number of times you can cross the x-axis is 2, right? We can have 2 single real roots. However, it doesn't have to cross it twice. It could bounce away. So it could just hit it and be a double root, right? So it's bouncing away. Or we could have imaginary roots. It never crosses the x-axis because the vertex is above the x-axis and it opens upward. Or you could have a vertex below the x-axis and opens downward, right? So all of these parabolas could be opening up or they could be opening down. It doesn't really matter. I'm trying to sketch what the description is here. So this one has 2 single roots here and here. This has 1 real double root, and then this is an example of 2 imaginary roots. So a cubic, if we wanted to have 3 single roots, it would be 1, 2, 3. So 1 single root, 1 single root, 1 single root. They all went through the x-axis. Okay, how about the next one? We're going to have a single root and then a double root. So I went through the x-axis and then I bounced off of the x-axis, or I hit the x-axis and bounce away. I just bounce off. Okay, what about the third example? We want 1 triple root. Remember, if you flip back to the beginning of the notes, the higher the multiplicity, so this has a multiplicity of 3 because it's a triple root, the flatter it gets. So it's just going to come through, flatten out. So wherever that value is, where it's a triple root, at that point because it's flattening out, but it's never really changing from increasing to decreasing. It's just going up, 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 up. It's just flattening out at the root. All right, how about this next one? 1 real, 2 imaginary. So it only crosses the x-axis one time, but here is where your imaginary roots are going to be, somewhere in there. All right, I want you to continue this next page on your own. So try, now that I've done the first couple of examples, I want you to pause here and just try them on your own. See how you do. There's infinite amount of pictures you could have, but you just want to see if you have the 4 single roots or 2 single, 1 double, 2 double. So you're just trying to understand what is a single root, what is a double root, what are imaginary roots, what are real roots, what's a quadruple root. So just pause and try that on your own. All right, have a look. You should have an idea. Here are some potential answers, right? We have 4 single roots, crosses the axis 4 times. 2 single, 1 double, crosses through, bounces away, bounces off, because it's 2 double. 1 quadruple just means it's super flat at that 1 singular root. Here we have 2 imaginary and 2 single, so here's a single, and then my imaginaries are up here somewhere. I have a 1 real double and 2 imaginary, so here's my double because it bounces away, and then you could put it, of course, obviously you know you could have the opposite end behaviors. It could be going up, up, or down, down, doesn't really matter. 4 imaginary roots means it's never going to cross the x-axis. We could have the W or the M shape, or it could just be one big, wide, looking something like this, but never crossing or touching the x-axis. So nice, ask your teacher questions if you're confused, but this is just try to get your head around single roots, double roots, imaginary roots, real roots, quadruple roots, etc. All right, so let's jump into some examples now. Now we're going to practice looking at an equation and sketching the graph. So let's look at example 1. It says sketch the graph of g of x, given that it equals 1/2 times the quantity of x plus 4 times x plus 1 times x minus 2. You have to do this. Label the x and y intercepts. So first of all, hopefully you're looking at this in intercept form and you're saying, great, my x-intercepts are -4, -1, and 2. So we're sketching, so I just do a quick approximation on the x-axis. There are my zeros at -4, -1, and 2. The next thing you want to do is find the y-intercept. So the y-intercept is when x is 0. So I need to plug in 0 for x. So what will the y-intercept be if I plug in 0 for x? So 0 plus 4 is 4, so you may not need to show all this work. You may just be doing this in your head, right? 1 times 4 times -2. Well, 4 times 1 times -2 is -8. 1/2 times -8 is -4. So my y-intercept is -4. Okay. So we kind of have an idea of what it needs to do, but really what I don't know and what you need to make sure you're checking on is the end behavior, right? What's happening as x goes to positive infinity and what is happening as x goes to negative infinity. So what do I have here? I have x. If I were going to expand this, I would have x times x times x, and then I have my leading coefficient of 1/2. So my first term with the highest degree is going to be 1/2 x cubed. This is an odd function with a leading coefficient that is positive. So if you go back and you look, an odd function and the leading coefficient is positive, well, I want to think to myself, okay, what happens if I put in a positive number for x? Then I'm going to cube it and multiply by a positive, so it's going to end being positive. My y value will be positive. If I put a negative value in for x, a negative cubed is negative, and negative times 1/2 is negative. So it's going to end, as x goes to negative infinity, my y value is going down to negative infinity. So now I just have to put it all together. These are all 3 single roots, right? They have a multiplicity of 1. So I have to go through the x-axis, hit my y-intercept, through the x-axis, and there is a sketch of my graph. It's not perfect, You know, we have no idea how high up this value is going to go right here, and that's okay. That's why we're sketching it. I didn't ask for this value. I don't have a grid. I'm not making you write a specific value there, right? It's just a sketch. So what do we have to have on our sketch? We have to have our x-intercepts of -4, -1, and 2, and we need to have our y-intercept of -4. Okay, try the second one on your own. Just go ahead and pause and try example 2. 2 times negative 1. Well, 25 times 2 is 50. 50 times negative 1 is negative 50. So I divide each side by negative 50. So A is actually equal to 5. So my last step is to actually identify the equation or the function for that graph, and this would be the exact equation for the graph, this particular graph here, because it had the point 3, negative 250 on the black graph. All right, try this one. If you want to pause and try it on your own, please do, or I'll just take you through it. But give it a go on your own if you can first, but you don't have to. Okay, so what do I see with this function? I see only two zeros. I see a 0 at negative 4, and I see a 0 at 1. But notice at this negative 4, it's flattening out. And so when it's flattening out, but actually going through the graph, it needs to be a bigger multiplicity than just 1. So that has a multiplicity of 3, or in other words, at negative 4, that's a triple root. So I'm going to build my function. I don't know what the leading coefficient or the A value is, what that dilation is, but I'm always going to write these equations in intercept form. So I have a 0 at negative 4, so I'm going to change that to positive 4. It's flattening out there, so that means it's a triple root, which means it has a multiplicity of 3. So that is why I have taken it to the third power. I have another 0 of 1, so I'm going to multiply this times x minus 1. It is just to the first power, so you don't even need to put that 1 there if you don't want to, because it just goes straight through the graph. I don't have any other zeros, so this is it. So the last thing I do is take the point that it goes through. It says it goes through negative 1, 162, or sorry, negative 162. So when the y value is negative 162, the x value is going to be negative 1. So I'm plugging negative 1 in for my x value, and now I'm just going to calculate. So negative 162 equals a times, well, negative 1 plus 4 is 3. 3 cubed is 27. 3 times 3 is 9 times 3 is 27. Negative 1 minus 1 is negative 2. 27 times negative 2 is negative 54. So I'm going to divide each side by negative 54, and then I'm going to divide that, and so that is just going to equal 3. Negative times negative, or sorry, negative divided by negative is positive, so that ends up being positive 3. So my final function is 3 times x plus 4, the quantity cubed, times x minus 1. Now, stop and ask yourself, does this make sense? My leading coefficient is positive. I have x to the third power times x to the 1 power. That would give me x to the fourth power with the positive leading coefficient. Is my end behavior such that that makes sense? Yes. It's an even degree, which means your end behaviors are the same. They're both up or both down. And my positive leading coefficient means that they're both going to be up. So yes, this makes sense. That is my final answer. So now this one, you should definitely pause and try this on your own. I'm going to do the same thing. And apologies, this says leave your final answer in standard form. We're never going to have you do that. So always leave your answer in intercept form. I'm not a fan of standard form. Do not worry about that. Just leave it in intercept form. We will never have you expand. Okay, go for it. Okay, last example, if you left it in intercept form, you could either put f of x equals negative 1 times x plus 4 times x plus 3 times x minus 1, or you don't really need to actually put the 1, you can just put a negative sign in front of those 3 parentheses. So how did I do it? I first got the 3 single roots, I listed them, then I used this information. When I plugged in negative 1 for x, I would get a positive 12 for y, and so I did all the math to figure out that a is equal to negative 1. So that's it. practice. There's lots of homework questions to practice, lots of practice in there. You might want to do just the evens or the odds to see if you're understanding it, and then save the rest for another day, like the day before the quiz or some other time to review. All right, ask your teacher if you have questions. Bye. To figure out